Depending on the identity of the solute, different solutions have different electrical properties. For example, in a solution of sodium chloride, better known as table salt, we would expect it to conduct electricity. On the other hand, table sugar, when dissolved in water, forms a sugar solution that does not conduct electricity. We call solutions that conduct electricity electrolytes, and solutions that do not conduct electricity non-electrolytes. In chemistry, we are interested in what is going on at the microscopic level. In other words, we want to know, in this solution, if I zoom in close enough, what is going on at the molecular level. It is important to understand that in order for a solution to conduct electricity, you need charged particles to be able to flow freely in the solution. And that means, in practice, that you must have ions in the solution. For non-electrolytes, which are typically molecular compounds, what happens is that the covalent bonds in each of the solute molecules do not break. They remain as neutral molecules in solution. Since there are no free-moving charged particles in the solution, there is no conductance. In contrast, in a solution involving a strong electrolyte, such as a solution of sodium chloride, what happens is that the ions dissociate. In other words, they separate and are separately dissolved in the water. For example, in the sodium chloride solution, you will see that the sodium ions and the chloride ions are separated. And therefore, we find that the sodium chloride solid crystal dissociates to form separate sodium ions and chloride ions. Let's look at two more examples of strong electrolytes. For example, sodium nitrate here can be found to dissociate to form sodium ions and nitrate ions in solution. Note that the polyatomic ions do not break apart in solution. The polyatomic ions themselves have covalent bonds within them that do not break when dissolved in water. Let's look at yet another example. This time we are going to look at barium hydroxide. In barium hydroxide, we have in one formula unit one barium ion and two hydroxide ions. Therefore, when it dissociates, it forms one barium ion and two hydroxide ions. It is important to note that the number of ions in a formula unit is the same as the number of ions that are dissociated off for each given formula unit. One remark needs to be made about acids. There are certain acids referred to as strong acids, and these strong acids dissociate completely when dissolved in water, much like, for example, sodium nitrate or sodium chloride or barium hydroxide that we've talked about already. However, many acids dissociate only slightly. Let's look, for example, at this solution of acetic acid. Here you find that while most of the acetic acid molecules remain intact, a small proportion of them dissociate to form H+ ions and acetate ions. When there's only slight dissociation, we refer to it as weak, and it is a weak electrolyte. It conducts electricity rather poorly. Note, importantly, that strong and weak in chemistry have nothing to do with the concentration. I can have a very concentrated solution of a weak acid, just as I can have a very dilute solution of a strong acid.